Hi there. Today we're going to be looking at logarithmic functions and their graphs. Previously we looked at exponential functions, and we're going to see that logarithmic functions are basically just the inverse of exponential functions. We've talked about the concept of an inverse. If a function has the property such that no horizontal line intersects its graph more than once, then a function has to have an inverse. And because of the graphs of exponential functions, look like this, it passes that horizontal line test, and that means, it's going to have an inverse, and the inverse of an exponential is called the logarithmic function. And if a was our base in the exponential, then a is also going to be the base in the logarithmic. So here's like legit from, I think, the Algebra 2 textbook, the definition of a logarithmic function. And so you can review all of these different pieces. Essentially, one really important piece is this idea that these are equivalent to each other, okay? That if you have, that didn't work, that if you have log base a of x equals y, that's the same as x equals a to the y. Notice that the base of your log is going to be the same as the base of the exponential. Notice that the exponent is going to be the same as the value of the log, and that the value of the exponential is equal to this piece right here. And I'm not sure if you've ever seen that before, but this piece right here, this x, this is called the argument of the logarithm, and I like calling it that so that we can have a conversation about what the argument should and shouldn't look like. But essentially, x is called the argument. And so notice that the argument of the log is the same as the value of your exponential. And so this function given by f of x equals log base a of x is called the logarithmic function with base a. One thing you may have seen before is just log x. When there is not a base that is present and you see the log function, it is understood to be base 10 that is there. And that's the common logarithmic function. And then another value that ends up being very convenient for modeling is this natural base e. And instead of writing log base e of x, because it's so common, they call it the natural log, and we write ln x instead. And again, I'm not going to call it ln x. I usually call it the natural log of x. Again, the gist is, and we looked at this, every logarithmic equation can be written in an equivalent exponential form and vice versa. Exponential equations can be written in logarithmic form. These are equivalent, and going back and forth between the two is very important. This is considered logarithmic form. This is considered the exponential form. And that's something that you guys reviewed in your summer packets. So we should be okay with the evaluating logs. I do want to remind you guys of some of the properties of logarithms. One of them is log base a of 1 equals what? Well, again, what this is saying, a logarithm is an exponent. So this is saying what exponent would I have to put on a to give me 1? And of course, what makes sense is this idea of 0. A to the 0 gives you 1, so log base a of 1 is 0. Here, it's saying, all right, with a base of a, what exponent would I need to put on a to give me a? And of course, we'd have an exponent of 1, so log base a of a is 1. If we have log base a of a to the x, again, it's asking, with a base of a, what exponent would I need to put on that to get me a to the x? And it looks like you just put a little x there, and so log base a of a to the x is x. Now, what if we have something like this? If we have log base a of x equals log base a of y. Well, notice that the two bases of the logarithm are the same. So wouldn't it follow that the two arguments would be equal to each other? So then we would say that x would have to equal y. And this is also true for any of the logarithms with the natural base, so the natural log. So the natural log of 1 is saying with a base of e, what exponent would I have to put on e to get 1? And that would be 0. The natural log of e is saying, okay, here's my base. The natural log has a base of e. What exponent would I need to get e? Well, just raise it to the first power. The natural log of e to the x is saying with a base of e, what exponent would I have to put on to make e to the x? And that would be an x. And then similarly, if we have the natural log of x equals the natural log of y, again, we have the same base. So what that means is that our arguments must be equal to each other. So that means that x has to equal y. So again, I want to just reinforce that the log function is the inverse of an exponential function. So let's maybe plot some points that represent the exponential function f of x equals a to the x. Well, one point would be 0, 1. Another point would be 1a. And then another point would be negative 1, 1 over a. And we know that it would have a shape something like this. We know that that was our exponential function with a horizontal asymptote at y equals 0. So again, these points, we had at 0, 1. This one was at 1a. And this one was at negative 1, 1 over a. So essentially, that's going to be our exponential function. We know that the domain was all real numbers. Our range was y is greater than 0. Again, that y-intercept was 0, 1, and our horizontal asymptote was y equals 0. Well, now let's take a look at what would happen if we were to graph this logarithmic function instead. Remember that an inverse, I'll write that here, that your inverse is a reflection over the line y equals x. And when you have a reflection in the line y equals x, essentially that means that you're switching your x and y. So that means instead of this 0, 1 that we plotted first, we would have 1, 0. Instead of 1a, we would have a, 1. Instead of negative 1, 1 over a, we'd have 1 over a, negative 1. And so essentially, then instead of having a horizontal asymptote of y equals 0, now we have a vertical asymptote of x equals 0. But again, notice that our points are all reversed. The x and the y switch spots. And if you drew the line y equals x, notice that if we graphed really nicely, then we could fold over that line and they would match up exactly. But that's what inverse functions are. It's a reflection over y equals x. And so when you do that, the x and y switch places. So now, notice the domain and range are switched. Now our domain is just x is greater than 0. And now the range is all real numbers. Now, instead of focusing on a y-intercept, we have an x-intercept that we can find. And we have a vertical asymptote at x equals 0. And when we graph these, we will always base it off of the apparent function of a simple logarithmic function, and then we'll do the transformations from there. Okay. One of the next questions asks us to find the domain. And one rule about the logarithms is that your argument has to be greater than 0. And so when they ask us for the domain of this function, essentially that means that our argument, that x squared minus 1, has to be greater than 0. And we've talked about solving quadratic inequalities. I believe we reviewed that in the summer packet. One way that you can do that is you could factor. And the factorization gives you critical points. And so then what we would want to do, we have a critical point at x equals negative 1 and a critical point at x equals 1. And when you have these critical points, you essentially are going to see what happens to the left of negative 1, between negative 1 and 1, and to the right of 1. And so to do that, we can just pick a number like negative 2, for example. So we have negative 2, and I think it's really easy to put it into this factored form. And just think about signs. All we want, you guys, is we just want this to be greater than 0. So we just need to find things that are going to make that true. So anyway, so we put negative 2 plus 1, that's something negative. Negative 2 minus 1 is something negative. A negative times a negative is a positive. So that means everything less than 1 will be positive. Let's do the same thing between negative 1 and 1. 0 is a nice number to choose. If we put 0 in here, 0 plus 1 is positive, 0 minus 1 is negative, a positive times a negative is a negative. So all the values between negative 1 and 1 are going to be negative. Now let's put a number greater than 1, maybe 2. 2 plus 1 is positive, 2 minus 1 is positive. So when I put 2 in, I get a positive value. That tells me everything greater than 1 will give me something positive. Well, let's decide which pieces of this we want. Okay, well, we wanted this to be greater than 0. So notice, first of all, that it wasn't equal to 0. So we know that these values at negative 1 and 1 should not be included. We'll think about those being open circles. And we want it to be greater than 0, which means we want them to be positive. So this part wouldn't work. We would only want these sections that were positive. And so notice that that's everything less than negative 1 and greater than 1. So what we can say then about the domain of this function is we can say that our domain can go from negative infinity to negative 1, and then also from 1 to infinity. And that would give us the domain of that particular function. Okay? So when you're finding the domain, remember your argument has to be greater than 0. And it could be quadratic, absolute value, any type of function could be in here. You just have to make sure that you know the solving techniques for those inequalities. So now let's get into the graphing part. Let's graph each function. Let's find the domain, the range, our vertical asymptote, our x-intercept, and then another point that we can get from the table. So if we have f of x equals log base 6 of x minus 2, again, our basic log function that we're going to graph is just this f of x equals log base 6 of x. So my parent, I'm going to put log base 6 of x. Now I want you to think about what really this means. If we have that y equals log base 6 of x, that's the same thing as 6 as our base raised to the y equals x. So sometimes people like to convert to this exponential form, and then instead we put values in for y in order to find x. But once you get more familiar with these logs, what you're going to find is that if you were to put a negative 1 in for y, that you're going to get basically the reciprocal of the base. So we have 1/6 negative 1 as a point. If we put 0 in for y, then anything to the 0 is 1. So then our ordered pair would be 1, 0. And if we put 1 in for y, then x is 6. So then 6, 1 is another coordinate. So what you're going to see with these log functions, you can go to the exponential and substitute the y values to get the x's. But one thing that might save you a little time is if you realize that if you use the reciprocal of the base, you get negative 1. If you use 1, you're going to get 0. And if you use the base itself, you'll get 1. Okay. So let's see what we have here. I don't see any reflections. I don't see any stretches or shrinks. All I see is this translation here to the right 2. So like we've been doing, I'm going to add 2 to every x coordinate, but there's nothing on the y, so I'm just going to have x plus 2 comma y. So that means I have 2 and 1/6, negative 1. I'm going to add 2 to 1 to get 3, 0. And I'm going to add 2 to 6 to get 8. And then I keep the y of 1. So I think it's always nice to start with the vertical asymptote. So our vertical asymptote essentially is going to be any translation here. Since this translated right to, that means our vertical asymptote that was at x equals 0 translates over to the right to be at x equals 2. And then after you have that asymptote, you can plot the different points. So 2 and 1, 6, negative 1 is about here. 3, 0, 6, 8, 1. And when you graph these functions, you're going to approach the vertical asymptote. Oops. You're going to approach the vertical asymptote. And then this, slowly but surely, just kind of keeps raising. So our domain is not all real numbers. What we see is that our domain is only going to consist of numbers to the right of this asymptote. So we can see that our domain is to infinity. And you can find that algebraically as well. You could say that x minus 2 has to be greater than 0, so x has to be greater than 2. Our range is going to be all real numbers. We've already dealt with our vertical asymptote. And our x-intercept is going to be when y is 0. Oh, good thing we have that here. From our table, we can see that our x-intercept is at 3, 0. If you ever need to find the x-intercept, which we'll practice, one thing you can do to find the x-intercept is you can let your function be 0. So we got this from the table, okay? Or what you can do is you can let f of x be 0. And then solve from there. So if we had 0 equals log base 6 of x minus 2, we basically can rewrite that in exponential form, and we can say that 6 to the 0 equals x minus 2. We know that 6 to the 0 is 1, and therefore we would know that 3 would have to be x. So again, we lucked out here because it was in our table, but know that you are able to find it algebraically by setting f of x equal to 0 and then using the conversion between exponential and logarithmic form. We said for additional point to pick something pretty from the table. We already picked the x-intercept of 3, 0, so maybe here I'll just list 8, 1. And that's essentially how we graph these logarithmic functions. Okay? Excellent. So let's practice some more. Oh no, we have here f of x equals the natural log of x plus 3 minus the natural log of e to the 4th. Well, what are we supposed to do? If possible, try to simplify. Do you see that this natural log of e to the 4th can be simplified? This is the same as the natural log of x plus 3. And then if we evaluate this, the natural log of e to the 4th is 4. So I'm really taking the natural log of x plus 3 minus 4. Now, remember when we had e to the x, we just used 2 points. And so the same is going to be true when we have the natural log of x. One of the points we used for e to the x was 0, 1. So let's use 1, 0 for e to the x. For the natural log of x. And another point we used in e to the x was 1, 2.7. So let's use 2.7, 1. So just use these in the table for your natural logs. And that's going to be our parent function. We're going to just ignore everything else and use the natural log of x. So for our natural log of x, we would have 1, 0. And 2.71. And let's take a look at what we have. Again, I don't see any reflections. No stretches or shrinks. But this is going to be a translation left 3, so I'm going to subtract 3 from my x's. And down 4, I'll subtract 4 from my y's. So 1 minus 3 is negative 2. 0 minus 4 is negative 4. 2.7 minus 3 would be, what, negative 0.3. And then 1 minus 4 is negative 3. So again, before graphing, maybe let's put our vertical asymptote on there. And again, the vertical asymptote is found by taking, x plus 3, basically that value, and setting it equal to 0. And so we can see that our vertical asymptote is going to be at x equals negative 3. And then similarly, if we're finding our domain, we want to say that x plus 3 is greater than 0. And we get that our domain goes from negative 3 to infinity. And our range would be all real numbers. So if we plot the points that were given, negative 2, negative 4, and negative 0.3, negative 3, again, that's why we like 3 points. 2 can be kind of hard. But we know we're going to approach our our vertical asymptote. And then we're going to go, again, eventually towards infinity. But let's talk about how we would find that x-intercept. So to find the x-intercept, that means that we could set our function equal to 0. So we could say, all right, 0 equals the natural log of x plus 3 minus 4. So I could add 4 to both sides to get that 4 equals the natural log of x plus 3. And then use what we know about logarithms to rewrite that. What does this look like in exponential form? Well, we know that the base of the natural log is e. So e to the 4th then would equal x plus 3. So that means that my x value would be e to the 4th minus 3. So what would that be as far as that goes? Well, if you look at the calculator, one place that you can find, if you're using the multi-view, for example, notice that the log function is here. So if we do second PRB to get to the log, notice that we can arrow over to the natural log, and that's where we can find our e raised to the power. So if I go down here, I can raise e to the 4th, arrow over, and then subtract 3, and then that gives me about 51.598. And so that means that that would be the x-coordinate of my x-intercept. So my x-intercept would be 51.598, comma 0. And obviously, then, you don't have to fix yours, but my pencil was breaking anyway. This is going to slowly but surely rise, and all the way over at 51.598, cross the axis. And then keep going. And then for the additional point, again, we can just glean something from the table. This one's a little prettier, so I'll use that one. Negative 2, negative 4. Okay. Let's see. Let's try number 3. In number 3, this is one like we have in the other problems that we might want to manipulate a little bit. Notice that in number 3, this is really like negative x plus 1. And we've talked about factoring out a negative. So let me even write it like that. So this is really the log of the opposite of the quantity x minus 1 plus 1. So again, just manipulate it so that we can really pull out those any stretches or shrinks or any reflections. So our parent function then would just be log of x. Notice that they don't have a base, which means that the base is 10. So that means that if we put the reciprocal of our base in, 1/10, we should get negative 1. So log of 1/10 would be negative 1. We can also put 1 in, and we'd get 0. Log base anything of 1 is 0. And then we can put the base itself in, 10, and then we'd get 1. So let's look, reflection. We actually do have a reflection. And because it's within the parentheses of, like it's what the function is operating on, that means that that is actually going to be a reflection in the y-axis, which means that we're going to make x negative, and we'll keep y. So then I'd have negative 1/10, negative 1, negative 1, 0, and then negative 10, 1. I don't see any stretches or shrinks, but there's a translation. After we factored out the negative, we can see that we'll translate right 1 and up 1. So negative 1/10 and plus 1 is 9/10. Negative 1 plus 1 is 0. Negative 1 plus 1 is 0. 0 plus 1 is 1. And negative 10 plus 1 is negative 9. 1 plus 1 is 2. So let's look at our asymptote. Our asymptote is going to be what happens when we set what's inside here equal to 0. And we can see that we do get that x equals 1. That's going to be our vertical asymptote. Similarly, to find the domain, oh, well, let me write the asymptote on here. I think it's fun to have the asymptotes in a different color, but you do you. And then again, we want our argument, 1 minus x, to be greater than 0. And so notice that we end up actually, remember when you multiply by a negative in an inequality, we reverse the inequality symbol, and we get that x is less than 1. So our domain is actually negative infinity to 1. And our range is still going to be all real numbers. If we plot our points that we get in our table, 9/10, 0, 0, 1, and then negative 9, 2. Then we can see that the domain and range, particularly the domain, that it follows from that. Sorry, my pencil keeps breaking here. But we're going to, again, approach that vertical asymptote. When it asks us about the x-intercept, I luck out and I'm like, sweet, I can tell that the x-intercept is going to be 9/10, 0. But I also just want to review with you how you can find it. You can also set the function itself equal to 0. Oops. So I can get that negative 1 equals log, the common log of 1 minus x. Remember, the common law has, what is the base? Oh yeah, 10. So I can rewrite this as 10 to the negative 1 equals 1 minus x. Well, 10 to the negative 1 is like 1/10. I can subtract 1 and I get negative 9/10 equals negative x, which means that x is 9/10. So that just confirms that our x-intercept is 9/10. Again, in a test situation, if it's in the table, you don't have to show this, but I just want to make sure you know when it's not in the table how you can find it. Let's see, and an additional point, I don't know, any of the other ones are good. I'll put the negative 9 too. That one's a little more fun. So there's that one, example 3. So next, let's look at example 4. This one actually has is probably the most fun because we have the most to do with it. So first, my suggestion would be to manipulate this a little bit. So this is like negative 2x plus 6. So not only do I want to pull out a negative, but because there's a coefficient of x, I'm going to pull out a negative 2. So I have 2 times log base 4 of negative 2, that would be what, times the quantity x minus 3, and then minus 4. So we can see that our function has a ton of different transformations. But let's think about our original parent function. Again, we're going to ignore everything, and it's just going to be log base 4 of x. So to get our values, again, let's think about the reciprocal of the base, 1/4. That would be negative 1 as an exponent. 1, that would be 0 as an exponent. And then 4, that would be 1 as an exponent. So let's look at what we would have. Reflection. We do. We don't have a reflection in the x-axis, but a reflection in the y-axis. So that means that we make x the opposite and keep y. So that would be negative 1/4, negative 1, negative 1, 0, and negative 4, 1. So again, that reflection tells us that we make our x's negative to reflect in that y-axis. So now we look at the vertical and horizontal stretches or shrinks. Well, look, this one is super fun. It has one of each. This 2 that is in front represents the vertical stretch. And so that means that's why we multiply the y by 2. We are stretching that vertically. However, when we see this here, remember that the horizontal stretch or shrink is the reciprocal of what we see. So when we see a 2 here, we are really going to be shrinking our x by a factor of half. So if I take half of negative 1/4, that gives me 1/8, well, negative 1/8. And then I multiply negative 1 by 2 to get negative 2. Half of negative 1 is negative half. 2 times 0, 0. Half of negative 4 is negative 2. 2 times 1 is 2. So again, remember that the vertical stretch that affects the y would be on the outside of the function, and that is what you see. If we see a 2, we're going to double the y. But on the inside of the function, if that's part of like the operator that we're dealing with here, then it's the reciprocal of what we see on the x. And let's see, we also have some translating. This looks like we're going to translate to the right 3 and down 4. So if I take negative 1/8 and add 3, that means I have 2 7/8 that are left that I have. Negative 2 minus 4 is negative 6. Negative 1/2 plus 3 is 2 1/2. 0 minus 4 is negative 4. And then negative 2 plus 3 is 1. 2 minus 4 is negative 2. So again, that's really the most tedious part, is just differentiating between all of those transformations and then making the points really clear. Well, the next thing we've been doing is looking at our vertical asymptote. Again, you can probably tell where it is, but you can always set the argument equal to 0 and find where that's going to be. And we see that our vertical asymptote should be at x equals 3. So we can definitely draw our vertical asymptote there. You can see that the domain then is also going to be affected, and it's either going to be less than or greater than 3. And so we could take the 6 minus 2x, set it greater than 0, and once again, you can see that we'll get that x is less than 3. So that means our domain is going from negative infinity to 3. Our range is all real numbers. And so we can plot some of these points. So 2 7/8, negative 6, 2 1/2, negative 4, 1, negative 2. And before I connect them, maybe I could find the x-intercept to see if it's going to be somewhere close over here. And remember, to find the x-intercept, I'm going to do that work down here. I'm going to set the function equal to 0. So I'll say that 0 equals 2 times log base 4 of 6 minus 2x minus 4. So I would add 4. I wouldn't rewrite yet because there's still a coefficient in front of the log. So let's divide by 2, and I get 2 equals log base 4 of 6 minus 2x. Now that we've gotten rid of all the peripherals there, we can rewrite this in exponential form. Let's see. So that would turn into, our base is 4. 4 squared equals the argument 6 minus 2x. Well, this is solvable. 4 squared is 16. So 16 equals 6 minus 2x. Subtract, divide. We get that x is negative 5. So that means that will be the x-coordinate of our x-intercept is negative 5, 0. And I know you guys wouldn't freak out, but some people are like, it's negative. But if you put the negative in, it's fine. Okay, like it will be a positive that you're taking the log of, so we're good. So let's plot that one. 1, 2, 3. Oh, wait, yeah. 1, 2, 3, 4, 5. So that's nice. That little x-intercept really kind of helps us with that graph, tells us where it's going to cross the axis. And then again, we'll approach that vertical asymptote. Cool. And then, oh, for the additional point, I guess we would just do, the prettiest one I see here is 1, negative 2. Okay. And that's essentially it. I guess because it looks like I have time, we'll do one more grown. All right, so remember the natural log of x. We don't have to play with this one at all. Our parent is going to be that y equals the natural log of x. Remember, the points we can use are 1, 0, and 2.71. Because remember, 2.7 is approximately e. So this one has a reflection. This one is a reflection in which axis? It's a reflection in the x-axis, which means we make the y-coordinate opposite. So 1, 0 will be the same, but this will turn into 2.7, negative 1. No stretch or shrink. And then this little plus 1 here just tells me I want to move my y up 1. So I have 1, 1, and 2.72 as points. So I can find the vertical asymptote. We were doing that. And you set the argument equal to 0. Well, look, the argument is just x here. So our vertical asymptote is x equals 0. So that's my vertical asymptote. Oh, sorry. This should be 0. I'm like, something doesn't sit right there. Negative 1 plus 1 would be 0. I was being positive over here. It's my fault. All right. So let's look at our domain. Our domain is that x is going to be greater than 0. So essentially, our domain will be 0 to infinity. Our range will be all real numbers. And our x-intercept from the table here, now that I've corrected that, should be at about 2.70. But again, I just want to practice with you real quick, finding it algebraically. You would say that 0 equals the opposite of the natural log of x plus 1. You could subtract 1 to get negative 1 equals the opposite of the natural log of x. Divide to get by negative to get 1 equals the natural log of x. And essentially here we are saying our base is e, our exponent is 1, so e to the 1 equals x. Well, that means that x is e, so that's going to be about 2.7. So we can plot, so we can plot 1, 1 and 2.70. And notice it looks like it's not, that it's approaching this way here. So we're going to approach the asymptote in this direction. And that makes sense because we said that there is a reflection in the x-axis. So that's why it has that different, that reflected look to it. And then additional point, I'll just have this 1, 1, 1. And that's it. So that's what you guys are going to be doing tonight. Using what you know about logs and the different transformations. to practice evaluating and transforming the graphs. So good luck, and we will talk soon. Thanks, guys. Bye.